Hi, hello everyone. Good afternoon and welcome to this course, Physics 1. This course is generally made for undergraduate level BTech degree students. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Baripur. You can personally meet me at college premises, ground floor physics lab. You can also send me a mail regarding your query or doubt on this topic or any video lessons if required at my given mail address. So my mail address is godphysics6@gmail.com or gopal.chakraborty_gkcem@gisgroup.org. I have a YouTube channel. The channel link is given here, so you can subscribe my YouTube channel for more videos related to the subject Physics 1 as per Macaut syllabus. So students, you may consult or you may check those videos, and if you find any problem, any doubt regarding any topic, you can contact me. Now the course pages are www.macautexam.net or www.macautwb.ac.in. You can find the syllabus regarding this subject Physics 1 is already uploaded in the university website. So the title of this course is Physics 1. The subject code is BSPH101. It is under the category of Basic Science course and it has a credit 4. So 3 lecture per week and 1 tutorial per week. This course is generally made for undergraduate level BTech degree students of first year. So students, those are coming for admission in BTech first year after passing out from 10+2 level. They have already a preliminary idea or knowledge about physics, this subject. So they have to study this subject in details in their first year course. So computer science, civil, mechanical, these departmental students will going to study this course in their odd semester, and alternatively electrical and electronics departmental students will going to study this course for their even semester, and that case the subject code will be BSPH 201. So for today's class I'll be your subject teacher, and now I will show you the topics that I will going to discuss today. As it is the second class of quantum mechanics, so the topic that I will going to cover are normalization condition, orthogonal condition, expectation value of position, expectation value of momentum, energy and kinetic energy, and the numerical applications on this topic. So these topics are under the module 4, that is quantum mechanics. So prerequisites for these topics are elementary idea of physics, fundamental idea of mathematical calculations. The corresponding course objectives are idea about normalization condition, orthogonal condition, no expectation value of position, momentum, energy. So after completion of this course, students will able to calculate normalization factor or normalization wave function for different cases. They will also able to calculate expectation value of position, momentum and energy for different cases. So these are the corresponding course outcome. Now before starting with today's class topic, I will like to remind you that in last class, in the first class of quantum mechanics, I have discussed why you will going to study this quantum mechanics, or what are the difference with the classical mechanics with the quantum mechanics. So in that case, I have explained in details that what is the wave function, what is the basic postulate of quantum mechanics, also what are the physical significance of that wave function psi, because you need to know, you must require that idea of all of these things for this today's class. So those who have missed in that class, please go through that video once again for today's class. It will be really helpful for you. So classically, the wave function is a second order differential equation in the space and time coordinate. Okay, so according to de Broglie, a material particle of mass m moving with velocity v is associated with a wave whose wavelength will be lambda equals to h by mv, or lambda equal to h by p, where p is the momentum. Since the particle has a wave aspect, there should be some sort of wave equation whose solution describe the space-time behavior of the particular function. So however, no way derivation of the wave function from the first principle. Okay, so it is therefore, however, we develop the basics of the knowledge of classical physics, but Schrödinger formulates some wave equation using de Broglie concept. Okay, this equation is basically known as Schrödinger wave equation, which gives you the same role as the Newtonian second law does in classical mechanics. So from the last class, you know that wave function actually describe the space-time behavior of the particle. It actually defines the position of the particle. Okay, and I have also discussed about the properties, basic properties of that wave function. So the function must be a single valued function, it must be a continuous function, and this wave function must be square integrable also. I have also discussed about the probability concept. So from there you can know that probability will be maximum or it may be minima. Okay, so for maxima means probability that value will be equals to 1, so it means the chance of getting the particle for that particular region will be maximum, and when the probability will be equals to 0, that means chance of getting the particle will be minima. So this is the concept of probability that I have discussed in my last day class, and I have also told you that every derivable function that is in quantum mechanics is operator, that means position, linear momentum, energy, kinetic energy. So these all are basically act as a operator, means a function. So from that part I have also shown you what is eigenvalue and eigenfunction. We have solved some problem. So these are the basic ideas that you need to know for this today's class. Okay, now I will discuss some condition that is known as normalization condition or normalization factor, which actually makes the wave function normalized. Now the normalization condition means to achieve that condition for which the probability of that particular given wave function will be maximum. That means the probability value that will be equals to 1. This is the condition of normalization factor, normalization condition. So to achieve that condition, suppose if you consider some non-normalized wave function, so to make it normalized you have to multiply this wave function with some constant. Okay, so as due to the application, due to the multiplication by some constant value, make this wave function normalized. That's why this constant is termed as normalization factor. Now I will show you what are the corresponding conditions. Here if psi in one-dimensional function, wave function, so psi is a function of position x and time t, that's equals to n into psi of xt. So where n is a complex constant such as psi n suffix n, a function of x and t, satisfy the relation. So here n is termed as normalization factor or normalization constant. So as we know, the probability that value is equals to integration minus infinity to infinity plus infinity mod of psi square dx, that is equals to, now if you replace the value of psi, you will get mod of capital N square integration minus infinity to plus infinity mod of psi square dx, that value must be equals to 1 to get the probability maximum. So this is the normalization condition. Now from there you can easily find out what is the value of normalization factor capital N. So mod of capital N square, that will be equals to 1 whole divided by integration minus infinity to plus infinity mod of psi square dx. So hence wave function is normalized if and only if the integration of minus infinity to plus infinity mod of psi square dx or mod of psi square dv, this all over the space remain finite. So this is a square integrability of wave function, and the value of capital N can be determined from the above equation. So this is the your overall normalization condition, and using that you can easily find out what is the value of that normalization factor. And now after calculating the normalization factor, if you multiply the non-normalized wave function by that normalization factor, so you will get a normalized wave function. Next condition, that is a orthogonality condition or orthogonal condition. So as I have told you that in case of normalization factor or normalization condition, the probability will be maximum. So for here the orthogonal condition, your probability will be minimum. That means the chance of getting the particle will be minimum for a given boundary region. So integration of minus infinity to plus infinity mod of psi square dx, that value should be equals to 0. That means probability will be minimum. I will show you the expression. So as I have told you, if a set of function u1 function of x, u2 also a function of position x, besides that integration limit a to b u suffix m star, so it is a complex conjugate of so into um of dx, that will be equals to 0 for m not equals to n. So then any two functions u suffix m and u suffix n are said to be mutually orthogonal in the interval of a to b. If on the other hand another condition, that means condition for normalization is also satisfied for m equals to n, so that means the integration a to b um star and un dx, that value is equals to 1. So this is satisfy both the normalization condition as well as orthogonal condition simultaneously, so this is called orthonormal condition. Okay, so that expression can be written as integration a to b um star un dx, that is equals to del suffix mn, where del suffix mn is called Kronecker delta. So that Kronecker delta value, that equals to 1 when m equals to n, and that value equals to 0 for m not equals to n. So then the wave function is said to be orthonormal, and it can be shown that any two eigenfunction corresponding to different eigenvalue are orthogonal. Now I will show you how we will prove the condition of orthogonality. So to prove that, let us consider u1 function of x and u2 function of x be two eigenfunction of a Hermitian operator a cap with eigenvalues a1 and a2 respectively. So then you can write a cap u1 function of x equals to small a1 u1 function of x, and a cap u2 function of x equals to small a2 u2 function of x. Taking complex conjugate of the above equations, we get a1 capital A cap star u1 star function of x equals to a1 u1 star function of x. a1 is a real, okay, and you can also write a2 cap star u2 star, that is equals to a2 u2 star. Now we now multiply the above equation by u2 function of x and integrate over all space. So if we take the integration over all space, we get u2 function of x capital A cap star u1 star of x dv, that is equals to a1 integration of all space u1 function of x u2 star function of x dv. Similarly, you can write for the second one. So second equation can be multiplied by the same procedure, and you will get all space integration u1 star function of x capital A cap u2 of x dv, that is equals to a2 integration of all space u1 star function of x u2 x dv. Since a cap is a Hermitian, so the left hand side from these equations are equal, so you can also equate the right hand side. So if you equate the right hand side and if you take all the term in the left side, so from there you can write a1 minus a2 whole into integration u1 star of x u2 of x dv, that's equals to 0, as a1 is not equals to 0 because these are the possible eigenvalues of that we have considered. So to satisfy, rest of the part is 0. So rest of the part is 0 means all space integration u1 star u2 of x dv that is equals to 0. So this is a condition for orthogonality and we have proved. Okay, now the another important term, that is expectation value, that is related to this wave function or this quantum mechanics. It is very important to know what is expectation value. The expectation value of a dynamical quantity is defined as the average of the results of a large number of measurements on independent identical system. Therefore, the system represented by identical wave function or a single measurement of each of a large number of identical systems. So this is the actual definition of expectation value, and the expectation value is the probabilistic expected value of a result or measurement of an experiment. So you can say that it can be thought of an average of all the possible outcomes of a measurement as weighted by their likelihood, and the such as it is not the most probable value of that measurement. Indeed, the expectation value may be 0 probability of occurring. So as example, measurement which can only yield integer value may have non-integer mean. So it is the fundamental concept of all types of quantum mechanics. So now, as I have told you that all the derivable, that's also the operators. So now the similar way I will tell you, you will going to find out what are the expectation value or the momentum or position, energy, etc. So I will show you step by step. Now the first one, that is expectation value of position. So expectation value of position, to describe this, suppose we are to find out the position of a large number of electrons, capital N. Okay, so capital N number of electrons are there, and all the electrons are described by the same wave function. So at time t, we measure the position of each electron between x and x plus dx. So this is the boundary. Then the probability that an electron will have position between x and x plus dx will be capital P, that is equals to number of electrons having positions between x and x plus dx, this whole divided by capital N. But the probability capital P of having position between x and x plus dx is, as we know, capital P equals to psi star psi dx, where psi is assumed to be normalized wave function. So the number of electrons having position between x and x plus dx is capital N psi star psi dx, and if x1 x2 up to xn be the positions of first, second or to up to nth number of electron, then you can write x1 plus x2 plus up to xn, that's equals to integration minus infinity to a, that is x capital N psi star psi dx, or x1 plus x2 up to xn whole divided by capital N, that's equals to minus infinity to plus infinity x psi star psi dx. But the left hand side, that's equals to within bracket x is called the expectation value of position of an electron. So the expectation value of position can be represented by within bracket x, that's equals to integration limit from minus infinity to plus infinity psi star function of x and t, x that is a operator, psi function of x and t of dx. So this last expression shows the expression for expectation value of position. Second one, the expectation value of momentum. So the similar way, how can you find out the expectation value of momentum? That is, if p x, because we have considered only in one dimensional case, so p of x be the x component of momentum of a particle, then the expectation value of px will be within bracket px equals to integration minus infinity to plus infinity psi star function of x and t px cap, that is a operator, linear momentum operator, into psi x of t of dx. So this is the expression of momentum value, expectation value of momentum. Okay, so where px is the operator corresponding to px, and that operator value is minus I h cut del x. So if you substitute that value, you will get minus I h cut integration minus infinity to plus infinity psi star del x of psi of dx. So this is the final expression of expectation value of momentum. So in my next class I will show you in details how we will calculate all the value of this operator. Okay, now next one, that is expectation value of potential and kinetic energy. So similar way, expectation value of potential will be within bracket v, capital V, equals to integration minus infinity to plus infinity psi star a function of x and t, potential operator, that is capital V, which itself function of x, psi of dx. So this is the expectation value of potential energy. Now to find out the expectation value of kinetic energy, so the process is same, that is within bracket k, capital K, that is equals to integration minus infinity to plus infinity psi star k cap, so that is a operator, kinetic energy operator, psi dx. So as we know, the kinetic energy operator that can be represented by momentum operator whole square by 2m, as p square by 2m is the representation of kinetic energy. So if you substitute that value, you will get 1 by 2m within bracket minus I h cut del x whole square, that is equals to minus h cut square by 2m del square del x2. So now the kinetic energy operator can be represented as minus infinity to plus infinity integration psi star within bracket minus h cut square by twice m del 2 del x2 psi dx. So this is the expression of expectation value of kinetic energy. Next one, the expectation value of total energy of an eigenfunction. So psi in function of r and t, the position and time, the energy of the nth eigenvalue is En, is real. So that can be represented by within bracket capital E equals to integration over a whole volume psi star E cap, that is a energy operator psi n of dv. So if you substitute the value of this operator, as you know, I h cut del t is the value of this energy operator. So if you substitute that value, you will get psi integration over v, that is psi star e to the power I e t by h cut, that is into hold in bracket I h cut del t psi n e to the power minus I ent into t by h cut of dv. So the exponential, that part will actually make it 1. So ultimately you will get en integration v psi star psi dv. So from there it can easily prove that the expectation value of energy that will be equals to the eigenfunction En. Okay, so this is the general procedure that when you are going to find out some expectation value of position or either momentum or some energy, so within a bracket you can write that is equals to integration over a given boundary, psi star, the given complex conjugate of the given wave function, psi star, that operator corresponding to that position or momentum or energy, psi of dv or dx as the boundary is given. So by that procedure you can easily find out the expectation value. Now I will going to solve some problems so that it will be very easier for you to understand how we will calculate the normalization factor condition or the corresponding expectation value as I have discussed. So the first problem, normalize the wave function psi. It is given psi function of x equals to a sine pi x by a when x is from 0 to a, and for outside that region the psi value will be 0. So the condition of normalization, as we know, the probability will be maximum. So integration of 0 to a, the limit is given here. So psi star psi dx, that will be equals to 1. Now if you substitute that value, so psi star means a star sine pi x by a dx. Okay, so if you multiply psi star with psi, so that will give you a star a integration 0 to a sine square pi x by a, as a star into a, that will again give you a square. So ultimately you will get a square integration 0 to a sine square pi x by a dx, that value will be equals to 1. Now put the value of sine squared theta, so that value will be half into 1 minus cos 2 theta, so make it a square integration 0 to a half of whole into 1 minus cos 2 pi x by a dx, that value equals to 1. So if you complete the integration, you will find that value a equals to 2 by a square, or capital A equals to under root 2 by small a. So this is the normalization factor, capital A. So if you now multiply that value with a given wave function, make it normalized. So your normalized wave function will be psi, that is equals to under root 2 by a sine of pi x by a. Second problem, show that the function psi equals to a to the power ikx plus b to the power minus ikx is an eigenfunction of the kinetic energy operator E cap. So we have the kinetic energy operator as ek cap equals to px cap square by twice m, where px cap is the linear momentum operator, has a value minus ih cut ddx. So if you substitute that value, you will get the kinetic energy operator as minus h cut square by twice m d2 dx2. Now E cap, that is equals to h square by 2m d2 psi dx2, that's equals to minus h cut square by twice m. Now substituting the value of psi after taking the second order derivative with respect to x, make it ik whole square a e to the power ikx plus minus ik whole square b e to the power minus ikx. So that makes it h cut square k square by twice m a e to the power ikx plus b e to the power minus ikx. So we can write E cap equals to h cut square k square by twice m into psi. So the above equation is an eigenvalue equation, and the psi is the eigenfunction corresponding to the kinetic energy operator having eigenvalue h cut square k square by twice m. So it is proved. So this is a numerical over that expectation value. Show that the expectation value of linear momentum for that wave function. So psi function of x equals to 2 by L whole to the power half. So that means under root 2 by L sine pi x by L and it will be within the region when the value of x will be from 0 to L, and otherwise 0 when x is greater than 1. So you have to prove that expectation value of linear momentum of this given wave function is a 0. Okay, so how we will prove? As we know, as per our formula, within bracket px, that is the expectation value of momentum, that will be equals to integration minus infinity to plus infinity psi star px cap, it is an operator, psi dx whole divided by integration minus infinity to plus infinity psi star psi dx. Now if you substitute the value of linear momentum operator, that is minus I h cut del x, so what you have find, you will get that you take the first order derivative with respect to x over that sine pi x by L, so that will give you half integration minus L to plus L 2 by L sine pi x by L into minus I h cut pi by L cos of pi x by L dx. So that will give you ultimately 0. So you get here your linear momentum, expectation value of linear momentum operator is 0. These are the important books that you may refer. The evaluation process are same. You have to appear for a 70 marks exam of end semester and internal exam for 30 marks. So all of you have hopefully understand and enjoyed today's class. In next class I am going to discuss about operator. So thank you.